Welcome back. This is section 8.5 on collisions, and this is section 7.5 in your textbook. We've already seen that momentum is conserved, that when you have momentum, which is the mass times velocity, so if a mass has a certain velocity, you have a momentum, and the momentum is going in the direction of the velocity, so in the same direction as the vector of the velocity. So if you have momentum in an object, and that object collides with another object, what you're going to see in this section is that if there's no other forces, if it's just the mass times velocity and it strikes something else that is a mass times a velocity, the same amount of mass and velocity is at the beginning of a collision as at the end. So the two momenta, I suppose, are added together. So whatever you have, the sum of them at the beginning is going to be the sum of them at the end. So here's your formula. The net momentum before a collision is equal to the net momentum after a collision. There are two types of collisions. We have elastic and inelastic collisions. If two things strike and there's no heat at all, now there's very few perfectly elastic collisions. Mostly what you're going to see elastic collisions is when we get to chemistry and we study gases. When two gas molecules strike each other, they're not going to lose energy when they strike. They're going to bounce off of each other with the same amount of energy that they had at the beginning. So that's a perfectly elastic collision, or at least the ideal gas is perfectly elastic. Most of the time you're going to have some transfer of heat. If two things smack each other, you're going to hear a sound that dissipates energy. You're going to have heat between them that dissipates energy. But the first idea, if you want to think of it as a concept, is that two objects could strike each other and 100% of the momenta of the first object would go into the second object. If one, say, is moving, the other one's at rest, all of it's going to transfer. The idea would be like a bowling ball hitting bowling pins. The idea would be that if it were perfectly elastic, the bowling ball would stop perfectly in its tracks, and then when it struck the pins, and all of the momenta would go into the pins. Well, since it's not perfectly elastic, the ball will continue to roll a little bit, but most of the speed would go into the pins. You've seen that if you've ever bowled. So here's the first example. If you've got a white ball that's not moving and a red ball that's moving, the red ball has momentum. The white ball has a mass but no velocity, so the momentum would be zero in the white ball. The red ball's momenta would be transferred into, now this is perfectly elastic, all of it goes in, nothing is wasted. So whatever speed the red ball, if they weigh the same, whatever the speed of the red ball, the white ball is at zero, would strike, the red ball would stop in its tracks, and the white ball would go on. You'll see this a lot on pool tables, where the cue ball is heavier, the same size but more dense, heavier, and all of the colored balls are the same size and weight. So one of those balls striking into another ball, you will see a pool ball stop in its tracks with all of it going into it. I've seen that too. Your second example here would be if they strike each other. So you've got both of them have a mass and a velocity, so you have momentum going together. And what do you think is going to happen? If you've got momenta, both of them together, either it will stop it or it's going to have enough that it will bounce. And if it bounces back, then both of the red and the white ball will go back to where they came from, exactly 180 degrees from their first. And then here's the last possibility. You would have the white ball's moving but slowly, and the red ball is moving fast, and the red ball strikes the white ball. What do you think is going to happen? Okay, remember, it's the sum of the momenta is going to be the same as the sum of the momenta at the end. What will happen is that the white ball will gain speed and the red ball will lose speed. So if you've ever been unfortunate enough to be rear-ended on the road where a car hits you from behind, you're going and the car behind you is going faster. What will happen is you will speed up and that car will slow down. The momenta in that car, whatever the offending car is, will transfer into your car. May it never happen to you. The second, of course, is the inelastic collisions. An inelastic collision is not just creating heat or sound or light, but many times will get tangled together. If you can imagine a train car behind a second train car and it hits, a lot of times the impact will actually couple the trains together and then they'll move as a solid unit. I was skiing once when I didn't know how to ski very well, and I plowed right into a guy, and both of us went down the mountain hugging each other. It was really embarrassing. I was like looking at the guy and saying, "Oh, please forgive me. I'm so sorry. I don't know how to ski." And we were, both of us, going down the mountain like one skier with 4 skis on. It was pretty embarrassing. All right, enough of that. Here's a situation where the train cars, you've got the same weight, each of the have the same mass. One's stopped going velocity 0, one's going 4 meters per second, and when they combine, the same amount of momenta, 4m momenta, is the same at the end. So 4m momenta with 2 m's will bring it down to 2 meters per second. So it would slow down, both of them going together but slowing down. That's an inelastic collision. So here's the example math-wise. If you've got the momenta, the net momenta before and after being the same, well, whatever the mass of the first car going 4 plus the mass of the 0, that's a total of 4m. Well, you're going to end up with 2m's times 2. So you'll end up with the same amount, 4m's, 4 meters per second times the mass. And then whatever your speed is going to be half the speed at twice the mass. So the 4 will go down to 2. Okay, so it would drop. Since you've doubled the mass and the momentum stays the same, it's conserved, you're going to have half the speed. So we'll see that most collisions are not perfectly elastic. Microscopically, in say gases, that would be an example where it's going to be perfectly elastic. Most cars and bicycle wrecks and any collisions that you would think of, you are going to have somewhat of an inelastic situation. Even if you were to drop a ball on the floor is going to make a sound. That's taking some of the energy away, plus the ball is going to be warmer and the floor is going to be a little bit warmer just because of the impact. And so 100% of that bounce is not going to come back. That's why if you were to bounce a ball and it bounces on the floor and then bounces up and then bounces again and then bounces again and again, each of those subsequent arcs are going to get smaller, okay? Because you're losing heat and you're losing, sound, and all of that is taking away from the energy of the collision, and so the second collision can't be as much as the first one. Okay, let's try a problem now. Consider a 6-kilogram fish that swims towards and swallows a 2-kilogram fish that's at rest. If the larger fish swims at 1 meter per second, what's the velocity after lunch? Okay, so you've got this guy is going in this direction. Okay, he's 6 kilograms and he's going at 1 meter per second. So what is his momentum? His momentum is 6 kilogram meters over seconds in this direction. Because remember, momentum has a vector. This guy is 2 kilograms and he is going 0. So what's his momentum? His momentum is 2 times 0, which is 0. So he has no momenta. Okay, so this is going to be 0 kilograms per second. What we're taught in this lesson is that the same amount, when you add them together, 6 plus 0 is all you've got to work with. If one guy is stopped, the only momenta that you have is the momenta of the fish that's swimming. Okay, so you've got 6 plus 0 equals 6. So you have 6 kilogram times meters per second, and that's all that you have to work with. So what's going to happen when he swallows the fish and now is not 6 kilograms, but 8 kilograms? Is he going to slow down, speed up, or stay the same? So here's the math. if the momentum is the same, okay, then it's going to be 6 times 1 is 6, 2 plus 1, 2 times 0 is 0. So 6 plus 2 is 8, okay? Now that's the mass, and 8 times the new velocity, because it's not going to stay the same. If he gets more massive, then his speed's going to slow down. So you're going to say V, 8 kilogram meters per second times V. When you get V by itself, you see that it went down to 3/4 of a meter per second. He was going 1 meter per second. He gains 25% of his weight, and he goes down by 25% of his speed. Okay, so now we've got the little fish swimming towards the large fish at 2 meters per second. So we've got this guy is 6. It's going at 1 meters per second that way. This guy is 2. It's going this way at 2 meters per second. So I've got, in the right direction, we've got 6 kilograms times meters over seconds. In the left, let's make it negative. We have 2 times 2. We have 4 kilogram times meters per second. So before we do the math, which direction and what do you think is going to happen? Which will win? We've got 6 going right and 4 going left. What do you think is going to win? I think the one on the left is going to win, and that the big fish is going to eat the small fish and still keep swimming, but his speed is going to go down because now his mass has gone up. He's still 6 plus 2. He's the 2 kilogram fish plus the 6 that he was is going to now be 6 going, but you're only going to have 2 left over. There's 2 kilograms left over. So 6 minus 4, you're going to have 6 kilogram meters per second left over, but his mass goes up. So he's going to go down. So let's look at the math. We've got 6 plus 1, and then 2 plus times negative 2. That negative 2 is showing you that it's going in the left direction, and we could set that up any way we want. But if right is positive, then left has to be negative. So then we'll end up with 6 plus 2 is the weight, because he's still going to be, it doesn't have a negative weight. He still has the kilogram mass times the new velocity. So we have 6 plus a minus 4. Okay, 6 plus a minus 4 is going to be 2, but then he's 8 kilograms times whatever his new velocity is. So when you divide that out, he's going to slow down by 1/4 or 3/4. So he's going to go down from 1 meter a second to the right down to 1/4 of a meter per second to the right. So did you learn anything? How does conservation of a momentum apply to collisions? Okay, the sum of the momenta is going to be the same before and after a collision.